Hey guys, welcome to the second part of vector spaces. So I think I'm going to need another lecture. So probably I'll cover 3 lectures instead of 2 on this chapter. Let me make one comment before I go and start the lecture. I looked at your exams. Most of you did do well the exams, but some of you did not provide too many details. So I'll be very picky together with my TAs when grading the exam. We will be very picky with the details. So I said at the beginning of the test, and I think I said it many times, you must write all details. Okay, let me just give an example. Some of you wrote the determinant, just the exact value without any proof. I told you, you need to provide a proof, the way you compute things and so on. Some others did provide all details, which was great. So anyway, the exam, from what I've seen, was a little bit easy for you. It was a 40 hours exam. Probably the final, I'll make the final to be harder than this. I can tell you that. Okay, with that being said, let me start the lecture.
Can I ask a quick question?
Yes, please.
Will it be at a certain time? Like, I know it's gonna be at a certain date, but will it be at a certain time?
It will be again the same. It will be a 24 hours exam. I will just send it. Probably I'll give you even more. It will be on August, I think August 5th, from what I remember, and you'll have to return it back to me on August 4th. I don't recall the exact date, but you will have to return it back to me, let's say on August 6th. I'll give you some, just like with the midterm exam. I think it was sufficient time to finish the exam, right?
Okay. Yes, sir. Thank you.
Yeah. Okay. Any other questions you have?
Is it August 6th or 4th or 5th? I thought
I don't
6th.
recall. It was on 6th. Okay, it was on 6th. It depends on what's written on my website and what did I tell you on my on the first lecture. So that's the date. I don't recall the date exactly at the moment.
The 6th.
Yeah,
probably
August
it's the 6th.
Okay.
Okay, August 6th. So probably I will send it to you on August 6th at midnight, just like I did with the midterm exam, and then you'll have to return it back to me in, I don't know, maybe 24 or 40 hours, something like this. You already use with this format. The final exam is worth the only difference is that the final exam is worth 40% instead of 30%. When you have 40%, probably I'll put maybe 5 problems in each. It's worth like 8%, 8 points. Anyway, I'll decide. But this is, so it's the same format as you are already used. Also, I'd like to make one quick comment. Some of you did not respect the instructions. Some of you send the exam to me separately and then to my TA separately. You need to send the exams. That's why I gave you those instructions, very clear instructions. When you send me the exam, you send to those emails to me and my TAs at the same time, so that we know exactly, okay, this guy sent the exam, you guys have it, because some exams will be graded by some TAs, some exams will be graded by other TAs. Then I will have to have a look. I will supervise everything. But anyway, so try to send the final exam to all of us at the same time. Okay, another thing that I want to mention is the following. What did I want to mention? I forgot. Anyway, maybe I just forgot. Anyway, maybe I'll remember and I'll tell you at the end. So now let's start with our lecture. And as you can see here, we started talking about vector spaces, right? We've seen what the vector space is, and so on. Now, I want to continue with this. I want to, well, just to remind you a bit about vector spaces. So let me remind you the definition. So you've seen that the vector space was that big thing with all those axioms and all those right. They need to satisfy something like this. All right, let's go back to vector spaces. And we have seen it in the case. So I want to go back, and we have seen this in the case of vectors, right? What kind of properties they need to satisfy. So let me go back. All right, properties of vectors in R2. You see, it has to be closed under the addition. The addition has to be commutative, associativity, identity, and so on, right? So the same thing will happen for an abstract vector space. Well, we will deal with vector spaces in Rn, not with abstract vector spaces and finite dimensional case, but the story will be the same. So let me quick remind you what the vector space is. So definition. And then we'll see a couple of examples because I forgot to, for some reason, I didn't put this in my notes. And I don't recall why, but anyway. So the definition is the following. Let V be a set on which two operations, and this is very important, two operations. And these two operations are vector addition and the second one is scalar multiplication. And scalar multiplication. So these are the two operations. So V is a set on which these two operations are defined. Right? If the following axioms, are satisfied, let's say, for every, let's say, every U and V, every vector is U and V, and W in V, right? So I have these three vectors in V, and every scalar, and when I mean scalar here, I mean real number. It can be a complex number as well, but let me keep this real number. And every scalar, scalars C and D, then V is a vector space. So under these axioms, this vector is the vector space. So this set V is a vector space. And the first one is, well, like we've mentioned, U plus V is in V. So anytime you add two elements from that set, the addition must be closed. So this is what we say closure under addition. The second one will be, like I said, U plus V equals V plus U. So this is what we say commutativity. Then the third one is, I hear a sound. No, this anyway. Anyway, the third one is associativity. U plus V plus W is U plus V plus W. This is associativity, right? Okay. And now we have some others. So we have the fourth one, well, there are, I think, 9 or 10, whatever. So the fourth one, V has a zero vector, Let's say this is 0. Doesn't anybody has his mic on? Because I keep hearing, I hear a sound. Yeah, some kind of notification, Discord I'm not using Discord, but sounds like somebody has. Daniel, I think you have your mic on. I think it's better for all of you to close your mics. I think that's. It was you. Okay, no problem. All right. Yeah, because it was a sound, and anyway, it doesn't bother me, but as long as it doesn't bother you, so that's fine by me. All right. So V has a zero vector. Let's call this 0, such that, and this is what it means, such that for every vector u, we have that u in V, we have that u plus 0 equals u. So this is what it means to be the zero vector. The fifth one, well, we need the opposite element. So for every u in V, there is a vector. There is a vector, and we call this vector negative u, such that u plus negative u equals 0, right? Okay, so these are the, okay, I want to point out that these are the axioms for, and let me be clear enough, these are the axioms for addition, so for vector addition. And now we will have some other axioms for scalar multiplication. So let's call this 6. For scalar multiplication, we have that very important C times U. By the way, I like to stress again that this C here is a scalar. So let me say it, scalar, and this is vector. If you don't like because I don't want to put arrows here since we're in an abstract vector space, but if you want to do so, you can do it. It's just a matter of preference or notation, the way you want to do it. You can put an arrow if you, in my case, I would like to put an arrow on vectors in Rn, but when I deal with vectors in a abstract vector space, I would like to keep it as a letter without any arrow, but I distinguish between these two. So C here in this case is a scalar, U is a vector. So this guy is in V. And you will see that this is not, don't take this for granted, because at some point you'll see when I'll give examples of vector spaces, you will see when I take an element and I multiply with another element, their multiplication is not in that space. Anyway, we will see an example. So this is what we call closure under scalar multiplication. Okay. The 7, we have this kind of this distributivity property. So this is C times U plus V, CU plus CV, right? So this is what we call distributivity. DVT. Another pro 8 is we have this distributivity, but this times with the scalar C plus D times U is C times U plus D times U. Again, this is distributivity. The first one was with vectors. The second one is with scalars. And 9, I hope I'm not forgetting anything. C, D, U is, okay. This is C, D. You multiply the scalars times U times the vector. So this is what we call associativity, some kind of associativity property with scalars, let's say. Although it's kind of an abuse of language what I'm doing, because there are also vectors here involved. U is a vector. And the last one, and this is very important to mention, is that wait, let me see. And the last one is U, 1 times U equals U. So you have the identity, the scalar identity. So this one here is a scalar. Pay attention, this is very important. Is not a vector. All right, so these are the axioms for these here, for what we call for the scalar multiplication. Okay, so you see, there's this list of 10 axioms. They need to be satisfied so that a vector is so that a set is a vector space. Well, the standard examples that I can, okay, let me give you quick standard examples of vector spaces. So examples, for example, R2 is a vector space, right? Or even Rn if you want. Or if you want the vector space of the set of all 2 by 2 matrices, let's say, for example. Let me denote this by, let's say, M22. So this is the set. So the set of all 2 by 2 matrices is this guy here. So it's a set of all matrices, let's say A, with A, B that look like this, A, B, C, D. And let's say that A, B, C, D are real entries. So this is the set of all matrices 2 by 2. You can consider this is just a set of, this is just an example of square matrices, right? But I can also consider the set of 2 by 3 matrices, right? And this is again a vector space. So I can consider also matrices that are non-square matrices. They're also related to some calculus. Probably you have taken calculus, I assume. The set of C infinity function, the set of continuous function, real valued continuous functions, again is a vector space. The set of polynomials, if you want, is a vector space, and so on. So there are plenty of examples. So almost everything you see is a vector space. But there are some which are not which is not a vector space. By the way, I have a question. Can you guys hear me well? Because it says that my connection is not stable.
Yeah.
Can you guys see and hear me well?
Yes.
Yes.
Okay. No problem. All right. Perfect. Yeah, just let me know when you see a problem. When there is a problem, just let me know when something is not okay. Good. Because it tells me here that I have the internet connection is not stable. So okay. Okay. All right. Okay, so these are the examples. These are the classical examples of vector spaces, but there are some which are not vector spaces. And let me give you an example. But before I go into that, let me mention something about a very important theorem. about properties of scalar multiplication. Let me be more specific. Properties of scalar multiplication. Okay, so the properties are the following. So let's consider V be any element, of the vector space V, right? So I'm taking V, this is a little v here, and this is the big V, right? So I'm considering, and let C be any scalar. Of course, when I say any scalar, I mean any real number. Then the following properties are true. Well, the first one is, and let me write them with color. So 0 times V is always 0. And pay attention here. When I say here 0, you see there is a difference between them. Okay, this is 0, the scalar. This is V, the vector. And of course, when you multiply a scalar by a vector, you will obtain a vector, right? So 0, the scalar, times V will always be 0, the vector. The second one is that C times 0, the vector, this time, pay attention. Again, this is the scalar. This is the vector. And guess what? This will be what? 0, the vector. The third one, let me put them here. The third one says if C times V, right? If the multiplication between a scalar and a vector is 0, and of course at this point you realize that this multiplication is 0, that 0 is 0, the vector, then you have two options here. Then C is 0, then the scalar is 0, or the vector is 0. Here is a vector, and here is a scalar. I want you to distinguish between them. And then another property, a fourth one, is that -1, let's say this, if we multiply the -1, the scalar -1 by the vector V, it will always be -V. So these are the operations. They're not very hard to prove, very easy to prove. And now, before I even talk about subspaces of vector spaces, let me give you some examples of sets that are not vector spaces. So examples of sets which are not vector spaces. And this is very important because I want you to see these kind of examples as well. Because you can imagine at this point that basically almost everything is a vector space. Not quite. And the first example I have in mind is the following. So I want to stress this again. These are examples of sets which are not vector spaces. The first example I have in mind is very easy. The set of integers. See, this is how simple it is. The set of integers is not a vector space. Can someone tell me why? Why is this not a vector space? Think about it for a second. Why is this not a vector space?
Does it have to do with the multiplication, like scalar multiplication?
Angel and Kobe, they have a point here. Okay, that's great. You see, you have something regarding the scalar multiplication. Yeah, exactly. So in other words, I can say something like this. What if I multiply? So I have a problem with the scalar multiplication. So let me write it with red. So if I have something like, let's say, if I multiply 1/2, right? Right. This is a scalar. I just pick a rational number. It doesn't matter. Times 1. And this is the vector. Pay attention. The scalars and the vectors are the kind of the same thing here. This is the vector, so which is an integer. So this is the vector, but in this case is an integer. I want to stress this out. This is very important. And when you multiply 1/2 times 1 is 1/2. But not. But what did we say? That this, if we look at the axioms, if we go back, what did we say? We said that the first axiom, when we have scalar multiplication, must obey what? The closure under scalar multiplication, right? Look at axiom 6. So anytime I multiply a scalar and I pick 1/2, just a rational number, the scalar can be any real. You can pick square root of 2 if you want, it doesn't matter. And I picked 1/2 times the vector, and I can pick any integer because my set is Z, is the set of all integers. The scalar multiplication is not closed, so I have something that is not in my space. Is not in, this guy is not in Z, so not an integer. So it was supposed to be an integer, so this is enough. It's enough for me. The negation of one of the axioms will just tear down everything. So this is not a vector space. So this is just a very easy example. There are plenty of other examples. Anyway, I don't want to, but I just wanted to give you a very simple example of a set which is not a vector space. All right, so now let's go and let's veer towards subspaces of a vector space, because we want to see what this means of a vector space. Sorry. Okay. And here we would like to address the following issues. So we would like to determine whether a subset of a vector space is indeed a vector space. We would like to address that. And also we'd like to determine the subspace of Rn. So these are our two goals. And let's look at subspaces first. So we want to see what the subspace is. What does your intuition tell you? What do you think a subspace is of a vector space? What do you think?
Is it like a subset?
Exactly. But okay, be more. Okay, yes, it's a subset. Yes, and what more? A subset that. Be more specific. So it's a subset that will satisfy the same set of axioms, just like the vector space. That's what it is. Exactly. So definition. Exactly. Share similar. Exactly. A subset that has the same properties with the vector space. So let's write the definition. So the definition of a subspace. Let me be specific here. Subspace of a vector space. So the definition is the following: a non-empty subset, and let's call this subset, let's call it like in the notes W, of a vector space, and this Can you guys hear me now?
Yes, sir.
Yeah.
I think we got disconnected for some reason. I don't really understand why. Anyway, I hope it's still recording. It says it is. Yeah, I think it's. It says that my internet is my connection is unstable. I don't know why it says this. Anyway, I'm not like I said. I'm not at home right now. I'm visiting in California, a friend of mine. So it's. I will blame him for this. But anyway, I hope it's recording. Let me just double check this to make sure that it's recording. Just give me. Yes, it is recording. Okay, great. So let's go back to. Okay, everything is fine now. Hopefully, we will not be sabotaged by the internet. Okay, so going back to the definition, we said that a non-empty, and I want to stress this again. The set must be non-empty because you will see that I need to verify this condition, which might seem trivial to you, but you will see that it can be tricky. So a non-empty subset W of a vector space V is a subspace of V when W is a vector space under the operations of vector addition and scalar multiplication. Addition and scalar multiplication. Scalar multiplication. Okay. Just like we said previously, I need to pick a subset of a vector space, and that subset needs to satisfy the same properties as the vector space. Let's, if we want to illustrate this better, let's give some examples. So examples. So I always want to illustrate, and when I give a definition or when I discuss a theorem, I always go by the example because I want you to see exactly how this notion or this theorem or whatever we're doing, I want you to see exactly how this applies to a concrete example. All right, so the example that I have in mind, let's say the example 1. This is a subspace of R3. So let me take this. W is the set of these vectors. Let's say what is x0 and x1 0 x3 with x1 and x3 in an R. This is a subspace. So this is affirmative of R3 with standard operations. So when I say with standard operations, I mean the vector addition and scalar multiplication, right? That's what I mean by standard operations. So let me mention this here. Vector addition and scalar multiplication. Okay. So let's see why this is a, why would you think that this is a subspace of a vector space? Let's look at the definition. I want you to look very, very carefully at the definition. It says that W must be a non-empty set or non-empty subset of a vector space V which is a vector space. So they need to satisfy those, oh my God, 10 conditions. But you will see that is not, it will be ludicrous for you to check all those 10 conditions. So it won't be necessary, but you will see a criteria for using that. First of all, I would like to ask you, let's look at the first part of the definition. Do you consider that this set is non-empty? And I want you to tell me, why do you consider this a non-empty subset? Why do you consider this a non-empty subset?
I mean,
Do
it
you
has
see
elements.
okay, be more specific. Can you give me an example of an element that it is in this set?
X1, 0, and X3. Is that all one element?
Yeah, this is okay. No, this is a general, but give me one specific element. Just tell me, like, look, this is it. For example, like Liliana says, the zero vector, right? Is there, right? 0, 0, 0. Belongs to R to W, correct? You just take X1 to be equal to X3, and that's it, right? So in this case, X1 equals X3 equals 0. These are real numbers, no problem. So indeed, when you have this element, when you have a set with at least one element in it, then you can say that this is non-empty. So you write it like this. Have you seen this notation before?
Yes.
Okay, so you're used with this notation, I hope. Okay, let me write it clearly here. W is a non-empty subset. Okay, now why do you think this is a subspace? First of all, we've seen the first part of the definition that is a non-empty subset. Okay, that's great, of a vector space. Oh my goodness. So the question I need to answer now is W a vector space? So I need to answer this question. So in other words, for me to answer this question, I need to verify all those 10 axioms. Oh my goodness, that will be a pain. That will be very painful for me to do so, so I'm not gonna do it. But instead of doing this, I'm just gonna, let me mimic something and then I'll tell you the exact what I did here, what I mimicked. So I wanna say this. So let me give you the long answer, and then I think the next theorem will enlighten everything. So the set is closed under addition, is closed under addition. And let me provide the following explanation. Because the sum of any two vectors, any two vectors of the form. So imagine you have something like x1, 0, x3, and you add with the following vector. Let's consider this to be an x, the vector x, and when you add it with the vector y, which is y1, 0, y3. So when you add these, and you know how to add vectors, we have seen this, you add their components, so you have x1 plus y1, you have 0 plus 0, which will be 0, and then you And then you have x3 plus y3. Guess what? This will be the vector x plus y, but this x plus y belongs also to w, right? Because it has a 0. It's the same type of vector as you have seen here, right, in the definition. So the second component is 0. So indeed, it is closed under addition. And now, so it's closed under addition. This is very important. And now I want to check another thing. Well, I would like to see if this set, so this is the first part, and the second part, the set is closed under scalar multiplication. This is indeed the second one, right? So the scalar multiplication, for example, may consider a vector, let's say x1 is 0, x3. So this is my vector x. And now I'm going to multiply this by a scalar, let's say c. So this is the scalar. And guess what? When I multiply by the usual properties of scalar multiplication, this will be c times x1, c times 0, which will be 0, and c times x3. Guess what? This is nothing else than c times x. And now, if you look at this vector that we obtain by multiplying by this scalar, by operating this scalar multiplication, belongs to w. Well, and I will say the following. One can also verify the other axioms. And I'll leave it to you as an exercise. Because if I'm verifying all of them, I'll go nuts. Will take us at least another 20 minutes. I'll leave it to you as an exercise, but the following theorem, fortunately, will give us, will just tell us that it's not necessary to verify all other axioms. It's enough to verify 2. And in fact, in this example, that's what I did. I verified only the most relevant ones. The closure under addition and the closure under scalar multiplication. So the theorem says the following. And this is a very important theorem. It's a test for a subspace. The theorem says the following. If W is a non-empty, non-empty subset of a vector space V, of a vector space V, then W is a subspace of V if and only if and only if, so this has a double implication, if and only if the closure conditions hold true. The closure conditions listed below are true. This is very important, the closure conditions. The first one, if U and V are in W, let me write in words, then U plus V is a U plus V, so the closure, the addition, sorry, is closed, is in W. So in other words, U, V belong to W implies that U plus V is in W. That's the condition, the first one. And the second one is the following. If U is in W and C is any scalar, then C times U is in W. In other words, U is in, U belongs to W, C is a real number, then this implies that C times U is in W. So that's the second condition. So guys, what I did, so this is the first one you need to satisfy, you need to verify, sorry, and this is the second one you need to verify. And that's enough to test if something is a subspace, right? If you go back, so let me, I want you to look at them again. Right, these are the two conditions. And if I go back with my example, but my previous example, you see, I've only verified two of them. And I told you to verify the others if you want to. But like I said, this theorem tells us that there is no point in verifying the others. It's enough to verify these two. If one of them fails, just like we have seen in the case of the integers, then we cannot talk about something being a subspace. And now let me give you another example, example 2. Example 2 is the following. And now let me consider a subspace of the 2 by 2 matrices. So for example, let W be the set of all 2 by 2, let's say, symmetric matrices. And I'll explain immediately. Well, in fact, you already know what a symmetric matrix is. Symmetric matrices. And we claim that W is a subspace of V, with V is M22, which is nothing else than the set of all 2 by 2 matrices. Right? So I'm taking this big vector space, the set of all 2 by 2 matrices, and I'm considering this subspace of all 2 by 2 symmetric matrices. So in other words, this W is a set of, let me write it explicitly, let's say A with that look like this, all matrices A that will have these, will look like this, and the entries A, B, C, D, let's say, are real numbers, and they have one property, A equals A transpose. So this is the set. So this is the set of all symmetric, of all 2 by 2 symmetric matrices. Oh my, again, it tells me that the internet connection is not stable, so I wouldn't be surprised if something similar will happen soon. We'll get disconnected. Anyway, let's hope that this won't happen. So this is the set of all 2 by 2 symmetric matrices, and we want to see that this is indeed a subspace. So we need to check two things. Okay, but before we even check those two axioms, what is the first thing we need to check? Can you tell me? The first question we need to address is what? Exactly. Like Morgan says here on the chat, we need to address the fact that the first question we need to answer is W a non-empty set, subset, whatever? That is the question I need to address, right? That's the first thing that came out into our in our definition. We need to have that subset to be non-empty. So what do you think? Is this non-empty? In other words, can you exhibit an element in this set? Just look at the set like W and tell me an example of an element. 2, 1. What do you mean 2, 1? Look at the elements. The elements in this set are matrices. 1, 2, 2, 1. Yes, exactly. Yeah, correct. I haven't seen that. So yes, you can, for example, take. The answer is yes. You can take A is 1, 2, 2, 1. Yeah. Or you can take A to be 0, zero matrix. O2, which is 0, 0, 0, 0. So there exist elements in this set. So the set is non-empty. Okay, great. Now, since we answered this question, and by the way, I want to tell you this. I will deduct points in a, let's say, in a final exam. If I ask you, show that this is a subspace, I don't know, I will give you a big problem. And one part of the problem is show that this little thing right here is a subspace of this vector space. And you'll be like, okay, I'm verifying these axioms, these two axioms. It's a piece of cake. If you don't prove that that subset is a non-empty, I will deduct maybe 1 or 2 points. Depends on the, I don't know, depends on how the grading scheme. But pay attention to this aspect because many people consider this to be trivial. But we cannot talk about anything if you don't prove that set is actually non-empty. It has elements in it. So there's no point in talking about properties about closure under addition or a closure under scalar multiplication if that set doesn't have any elements in it. Okay, but in this case, in the case of 2 by 2 symmetric matrices, it's clear that we have elements here. And now, since we're convinced that this is a non-empty subset, I want to see why is this a subspace of M of the vector space of the set of all 2 by 2 matrices. So we need to check, we need to verify those two axioms. So we consider 2 elements, let's say, 2 elements of W. And when you consider these 2 elements of W, let's say A1 and A2, I want to denote them like this because these 2 elements are matrices. Keep that in mind. So, right? They're symmetric matrices. In other words, where A1 and A2 are symmetric matrices. Okay, this means that A1 equals A1 transpose and A2 equals A2 transpose. Now I want you to tell me what's going on with the addition. What do you think? Do you think that, so the first thing, closure under addition. In other words, if we take A1 and A2 in W, does this imply that, and I put a question mark here because I want you to see if we want to answer it, does this imply that A1 plus A2 is in W? That is the question. What do you think? Is this true? Well, let's see. This means that, what does this mean? This means that if A1 and A2 are in W, which means that if the translation of this is if A1 and A2 are symmetric. Does this imply, and this will, I put here a question with that, A1 plus A2 is symmetric? In other words, we know that, let me even translate this. In other words, if A1 equals A1 transpose and A2 equals A2 transpose, does this imply that A1 plus A2 yes, A1 plus A2 equals the same as A1 plus A2 transpose? That is the question. Well, very easy to see. Well, what do we know about the addition? We know that A1 plus A2, since we know that A1 is A1 transpose, is the same as A1 transpose plus A2 transpose. But we know from the properties of the transpose of a matrix, and we have seen that previously, that this is nothing else than just A1 plus A2 transposed. And indeed, this is, yes. So yes, this is true. What about scalar multiplication? So the first one, closure under addition, is true. What about closure under scalar multiplication? What do you think of this? So this is the same thing. If I have a scalar C, let's say a real number, and I have a matrix in W, does this imply that C times A belongs to W? That is the question. In other words, if we want to translate this in equivalent form, this says if C is a real number and A equals A transpose, does this imply that C times A is the same as C times A and everything transposed? That is the question. Well, again, that's easy to see. If we look, so if we consider C times A, let's look at this. And this is the same as C times, since we know that A belongs to W. In other words, A is a symmetric matrix. This is nothing else than C times A transpose. But by the properties of the transpose of the matrix, so I go back to the properties of the transpose of a matrix, this is nothing else than just, and we know that under scalar multiplication, this is nothing else than CA times A, everything transposed, which is exactly this. So again, this property is verified as well. This one here. All right, by applying the subspace theorem, so the test for a subspace, this is indeed, so it follows that W is a subspace of V, which V is the set of M2 to the set of all 2 by 2 real matrices. So that's what you need to check. For example, well, there are plenty of other examples. So you can take the set of, I don't know, I'll leave it to you as an exercise. Let's say, just think about it. Maybe, so for you as an exercise, is the subspace, is the subset of all, let's say, invertible matrices a subspace of, let's say, n by n, the set of all n by n matrices. I'll leave it to you as an exercise to figure it out if this is the case. So we'll leave it as a question mark. And you know what the invertible matrix is, what an invertible matrix is. But now I want to consider also a counterexample, something that is not a subspace. And the example that I have in mind is the following. So example, let's consider the set of all singular matrices, the set of all. So of all singular, when I say singular, I mean non-invertible. Non-invertible matrices. Okay. So this is the W. So is this and let's take. Okay, I'm just gonna consider. Let's take 2 by 2. Of all singular, let's say 2 by 2 matrices. So this is a set of matrices which look like this: A, B, C, D. When I say singular, I mean the determinant of A, which is given by A times D minus B times C, is 0. So in other words, AD equals BC. The question is W a subspace? That is the question. What do you think? But before I even go and talk about this and see why this is not, first question I want to address, is this an empty set, first of all? What do you think? Is this a non-empty set or not? Well, thank God it is non-empty, right? There are plenty of matrices out there which are singular, right? Which are non-invertible. When I say plenty, I mean infinitely many. You're just getting, let's say W is non-empty. Since we can, for example, if you take A to be the zero matrix if you want. The zero matrix has determinant 0. Right? There is an element in W, so it is non-empty. That's a very important thing. But now the question is, does this subset satisfy those two conditions? That is the question. So the two conditions I'm talking about from that theorem are closure under vector addition and closure under scalar multiplication. So in other words, which one do you suspect that will fail? What do you think? Multiplications, the scalar multiplication. So do you think that will influence that much? For example, if I have a matrix, so let's see. If you have something like a matrix with determinant, okay, let's say we have, so the scalar multiplication, let's check both of them, we'll see. But let's start with the scalar multiplication. Pay attention for that. Okay, let me talk a bit of logic with you. When you try to negate something, suppose, I don't know, I don't want to give a real life example. Who knows, maybe I become political or something. when you, okay, let me put it this way. When you try to negate, to say that something is good or bad, and you have a set of axioms, 1, 2, 3, it's enough to negate one of them. That's it. For example, you describe that this person is good if this person has this traits, 1, 2, and 3, right? That's the definition of good person. If you negate one of them, it's enough for you to conclude that that is not a good person. The same happens here. So this is kind of a logic. So when one of these two axioms, in our case, is not satisfied, then you can draw the conclusion immediately. So I don't care what happens to the other one. If I show that one of them is not valid, then that thing doesn't hold true, right? So in my case, it can happen. So in this case, it can happen that the scalar multiplication to be true, but the vector addition might not be true. So the scalar multiplication. So let's see. If we have a C times A, right? So do you think this is if a matrix A is singular? So let me be more specific here. If A is singular, does this imply that C times A is singular? That is the question. What do you think? So Morgan says that this might not be true. Well, let's see. What do you think? In other words, determine, let's see what this means. So now we're going to, this means that the determinant of A is 0. Does this imply that the determinant of C times A is 0? What do you think? Well, it's quite clear, right? If a matrix, because the determinant of this is nothing else than C, in our case, is 2 by 2 C squared times the determinant of A, which will be 0. So this property is satisfied. Bad luck here. Now, since this is satisfied, but I said that this is not a subspace, this implies that the other one will not be satisfied. So I was not looking at the right property. Let's look at the vector addition. So indeed, we have closure under scalar multiplication, but maybe we don't have closure under vector addition. In other words, if let's consider A, B, two matrices in M2, 2, right, with real entries, and A, B are singular matrices. Does this imply that, and I put here a question mark, that A plus B is also singular? And the answer is no. And I told you at this one review session, when you have, when you want to prove something, right? You prove it. If this happens, then show this, you prove it. You write the proof. But when you're like, show that this property doesn't hold true, well, or if you can, or if it's a question like, if these are singular, does this imply that this is singular? Well, if the answer is no, it's enough for you to provide an example. So the answer is no. And what we can do when we say the answer is no, is we say the following. In other words, we can come up, we can cook up some 2 by 2 singular matrices. Let's say A and B with determinant of A equals determinant of B equals 0, such that, guess what? Determinant of A plus B is not 0. And if I put my hands on one such example, then I'm done. And let's consider, so consider the following matrices. Consider A, and let me pick one of them that is singular. So let me 1, 0, 0, 0. And now let me take B to B. Well, so I want another one. Let's take 0, 0, 0, 1. Okay, that's great. Clearly, determinant of A is the same as determinant of B. I think I gave this example already in one of the review session. I think the question was, or something similar, a very similar example. The question I believe was, it was in the second review session, the one that I recorded after, says that it showed that there exist matrices 2 by 2 such that the determinant is additive. Usually it's not additive, but there you can come up with some examples for which it is, right? But it's not, my point is that the determinant is not additive for all matrices. And I believe this is the example that I gave, or something very, very similar. Anyway, in our case, so the determinant of A is the same as the determinant of B and is 0. But now if I look at A plus B, this is nothing else than just, let's add them. And this will be nothing else than just 1, 0, 0, 1. Perfect. This is nothing else than just the identity. And the determinant of A plus B is the same as the determinant of the identity. And this is nothing else than the determinant of the identity, you know it's 1. Surprisingly, with different, 1 is different than 0. So this means that A plus B is not singular. So this implies, so this is the second one, the vector addition that is not closed. So the moral is the vector addition is not closed. Well, if this doesn't happen, then we can conclude that, so one of the two axioms doesn't hold true. W is not a subspace of this vector space VM22, which is the set of all 2 by 2 real matrices. You see, not all subsets of the set of matrices, for example, are subspaces. And here I gave you an example. And there are plenty of other examples, and I would like you to look at the notes. Let me just mention another one, which is very simple, and I'll leave it to you as an exercise. Why this is not a subspace. And I will consider a subset. This is a subset of R2. And this is a subset that is not a subspace. Keep that, pay attention to this. And the example is the following. Let me consider this W to be the set of all vectors, x1 with components x1 and x2. And they have the following property. x1 is non-negative and x2 is non-negative. This is not a subspace. Wow. So I'm considering the components to be non-negative, and this is not a subspace. You'll see why. It's actually very simple. In fact, let me just say it. It's just one word. This time, so Morgan gave the example of the scalar multiplication, which applies in this case. For example, let me consider this element. So the scalar multiplication is not closed. Is not closed. In other words, we don't have the closure for scalar multiplication. So let me consider this point. Let's say 1, 1 in W. And now, so clearly this is 1 and a 1 is in W because 1 is positive, 1 is positive, so I have no problem with this. And now I'm going to multiply by a scalar, let's say -1. So this is any real scalar. And I'll multiply by this vector, 1, 1. And you know how to multiply a scalar by a vector. So you multiply each component. So this will be what? This will be -1 and -1. Again, it says that connection is unstable. Can you guys hear me? Can you hear me, guys? I don't hear anything. Anyway.
I can
Yeah,
hear
we
you.
can.
Yeah, we can hear. Okay, because it says that the connection is unstable. And all right, so when we multiply with this real scalar, -1, I'll have -1, -1. But this doesn't belong to W because look how W was defined. The components must be non-negative. Well, here we go. It's not. All right, I think I'm going to stop here. I dwelled too much on this, and I think I lost some time. Next time, I will start talking about spanning sets, linear independence, basis, and so on. Next time, I think it will be. I will tell you. Probably it will be on Thursday evening or something like this, or Friday. I'll decide when. It will be optional for you if you want to listen to the lecture. I will do it anyway, even if I don't have, even if none of you will be online. I'll stop here. Thank you very much, and let me take the attendance. So, but before that, let me stop the recording.